What if the empty space between stars isn't empty at all? What if the universe is woven together by an invisible framework? A cosmic web of mass we can't see. This isn't an accident, it's a clue. These arcs of light are evidence of a powerful, unseen structure bending the fabric of space itself. The James Webb Space Telescope is now translating these beautiful distortions into a map of the hidden universe. Picture this. Webb stares into what appears to be empty space. Then, faint arcs of light emerge, wrapping around invisible mass, almost like a lens bending distant beams. In this video, we'll explain how those arcs form, how scientists translate them into maps of hidden mass, and why Webb is uniquely powerful for this work. These arcs aren't mistakes. They are strong evidence that mass bends light on its way to us. The arcs reveal where unseen matter lies, but interpreting them requires careful modeling and independent checks. When traced precisely, they outline filaments of invisible structure that form the universe's framework. We'll walk through the steps scientists use: imaging, redshifts, and lens models, to turn arcs into three-dimensional maps of the cosmic web. And to understand why that matters, we first need to think about what this web of the universe actually looks like. The universe woven like a web. If we widen our view, a different picture of the universe comes into focus. A vast and connected network, often called the cosmic web. Instead of random scatter, galaxies line up along the tendrils of structure that stretch across billions of light years. At the densest junctions sit galaxy clusters, while long filaments link them together. Between these strands are huge voids, regions almost completely empty of galaxies. This is the largest structure known, and everything we see, planets, stars, galaxies, rests within this framework. The mainstream consensus is that ordinary matter makes up only a small fraction of this scaffolding. Most of it is dark matter. Dark matter is a type of mass that does not emit or absorb light, but reveals itself through gravity. Without it, the web's filaments would not exist. For astronomers, this is a central challenge. Telescopes can only observe the luminous matter, while the bulk of the framework remains unseen. It is like noticing only the points where something luminous sticks, but not the threads connecting them. To make this idea clearer, think of a building under construction. The visible walls and windows are like galaxies shining with starlight, but the steel beams that support them all, dark matter, go mostly unnoticed. The universe relies on this scaffolding. Galaxies arrange themselves along those filaments, but mapping the skeleton itself requires strategies beyond ordinary astronomy. Large cosmological simulations help bridge the gap between what we see and what we think underlies it. These simulations track how particles and gravity shape matter over billions of years. The result is a virtual universe where clear, web-like filaments form naturally, with dense nodes where galaxy clusters collect. Astronomers then compare these simulated webs to surveys of visible galaxies. These matches are striking, but they do not eliminate a persistent problem. The dark matter filaments themselves cannot be directly observed to confirm the models. We are left inferring their structure by how galaxies group, which always involves uncertainty. Our current telescopes can map galaxies to great detail, but those galaxies are only the illuminated tips of a much larger iceberg. They mark points in the web, but leave the overall distribution of mass hidden. Trying to infer the entire pattern of the cosmic web only from visible galaxies is like attempting to reconstruct the full shape of an iceberg by tracing the small section floating above the waterline. Most of the bulk lies beneath the surface, invisible but fundamental. For that reason, the deepest question is how scientists can uncover the hidden shape directly. The answer lies in nature's own diagnostic tool, gravitational lensing. This phenomenon occurs when the mass of something, whether a galaxy cluster or a more diffuse concentration of dark matter, bends the light traveling from more distant galaxies. To us, the background galaxies then appear subtly stretched, magnified, or displaced. In effect, the distorted shapes of galaxies become traces of how mass is distributed along the line of sight. Both ordinary matter and dark matter leave their mark because neither needs to emit light to bend it. The key takeaway is that the structure of the universe is not flat or random. It has an ordered geometry sculpted by mass over cosmic time, but seeing that structure depends on methods that look for distortions in light rather than direct brightness. Next, how light records this hidden structure. Gravitational lensing acts as the diagnostic tool that turns invisible mass into observable distortions. Light as a cosmic detective. Light becomes an investigator when it crosses the universe, carrying hidden information about the structures it passes. This is the starting point for what scientists call gravitational lensing, mass bending space-time so that light paths curve. The bending is not just a theory. It changes how distant galaxies appear to us, producing stretched arcs, multiple images, or in rare cases, rings of light around a foreground cluster. The most striking version, an Einstein ring, forms only when source, lens, and observer line up perfectly. Those complete circles are uncommon, but the principle holds even when alignment is less precise. Most of the time, galaxies appear slightly warped, tilted, stretched, or elongated into arcs. To the human eye, a lensed galaxy may look almost ordinary. But when astronomers measure hundreds of galaxies together, repeating distortions come into focus. Each shared stretch or twist points back to unseen mass between us and those galaxies. Well-known cluster images make this effect clear. Able 2744, sometimes called the Pandora cluster, is a textbook case. Its field of view shows dozens of pale, curved arcs wrapping around its brighter members. These arcs are distant galaxies behind the cluster, their shapes redirected by the cluster's gravity. The cluster itself works like a magnifying lens, making galaxies billions of light years away, visible when they would otherwise be far too faint. Crucially, the pattern and placement of those arcs reveal how much mass sits inside the cluster and where that mass concentrates, whether luminous or dark. The strength of lensing is that it outlines mass directly. Stars and gas only trace part of the picture, but lensing shows the total gravitational effect. An everyday analogy is a window pane with imperfections. Looking through rippled glass, the outside view appears warped, but the warping pattern encodes where the glass is uneven. Lensing works the same way. Warped light acts as evidence of how matter in the foreground distorts space itself. Deep field surveys add still more power. Long exposures collect hundreds of faint galaxies in a single patch of sky. Close inspection shows that some are curved, mirrored, or stretched, signatures of intervening matter. These images often record arcs aligned with structures that formed billions of years ago, becoming natural signposts for the universe's large-scale pattern. By repeating this process across different sky regions, astronomers start to piece together how invisible matter arranges itself on cosmic scales. Turning distortions into usable maps requires more than inspection. Scientists follow a stepwise process. First, they confirm which galaxies sit behind the lens using redshift, the measure of how much light has been stretched by cosmic expansion. Second, they measure the shapes and positions of those distorted galaxies with high precision. Third, they run lens models, mathematical reconstructions of the mass distribution most consistent with the observed arcs. Each stage narrows down the location and amount of mass responsible for bending the light. Combining many arcs and many redshifts builds up a three-dimensional picture of how matter is woven into clusters and filaments over immense distances. These results turn small smudges of light into evidence for the skeleton that holds the visible universe. Still, caution matters. A single arc cannot prove the path of a filament by itself. They are strong probes of hidden mass, but a robust map requires many arcs at varying depths, plus cross-checks with other observations. The consensus view is that lensing provides one of the most direct and reliable ways to trace dark matter's distribution, while uncertainties remain about fine details of the geometry. Improved resolution and deeper imaging continue to sharpen these reconstructions. Yet even the best older instruments face limits, arcs too faint to identify, background galaxies lost in dust, and redshifts too uncertain for robust models. Pushing mass maps further depends on tools capable of detecting fainter shapes, resolving them more sharply, and confirming their distances with high accuracy. That is why the next step in this story turns to how a newer observatory makes those advances possible. Why Webb sees what Hubble couldn't. The consensus reason Webb is making a difference is straightforward. It can see in infrared light, while Hubble worked mainly in visible and ultraviolet wavelengths. Infrared allows astronomers to detect galaxies hidden by dust or stretched so far by cosmic expansion that their light shifts out of the visible range. What once appeared as blank sky in Hubble's images now reveals faint arcs and background galaxies shaped by lensing. By capturing these longer wavelengths, Webb adds entire layers of detail to cosmic maps that were previously incomplete. Before Webb, many populations of faint, redshifted, or dust-obscured galaxies were difficult or impossible for telescopes like Hubble. to study in detail. Some galaxies sat behind thick curtains of foreground dust. Others were dimmed so severely that their signals fell below Hubble's sensitivity. As a result, the arcs formed by gravitational lensing often appeared only partially, or not at all, in older images. Scientists could predict where lensing should occur using models, but without faint galaxies acting as tracers, the mass maps built from those data remained patchy. Webb's near-infrared camera, or NIRCam, immediately improved the situation. Operating in the near-infrared range, it combines sensitivity with sharp resolution, allowing faint arcs to stand out cleanly around massive clusters. The function of NIRCam is not to create arcs, but to record them in enough detail that each warped galaxy can be measured reliably. Small differences in shape and orientation matter, because they indicate where mass sits in front. By making these forms precise rather than blurred, NIRCam increases the number of dependable traces of mass. The Mid-Infrared Instrument, or MIRI, extends Webb's reach further still. Mid-infrared wavelengths come from galaxies so distant that their light has travelled for most of cosmic history. These early systems radiate in ranges completely beyond Hubble's detectors. With MIRI, astronomers can study galaxies from just a few 100 million years after the Big Bang. In lensing terms, this means background galaxies are available at extraordinary depths, adding more reference points against which to map foreground mass distributions. The wider the pool of background sources, the stronger the map of the hidden cosmic web becomes. But imaging alone does not resolve the distances of galaxies. A background arc must be proven to lie farther away than the lensing cluster. Webb's near-infrared spectrograph, or NIRSpec, provides that confirmation. Spectroscopy divides a galaxy's light into its component wavelengths, revealing a redshift that serves as a distance marker. When NIRSpec identifies a lensed galaxy's spectrum, astronomers can confirm that it sits behind the cluster responsible for bending its light. Each measured redshift becomes a secure coordinate in a mass model, replacing visual guesses with quantitative evidence. Together, these three instruments, NIRCam with high-resolution near-infrared imaging, MIRI extending sensitivity into the mid-infrared, and NIRSpec measuring redshifts, expand the pool of arcs and background galaxies available for mapping. They do not eliminate uncertainty, but they multiply the number of usable data points. That multiplication transforms lensing studies from relying on scattered visual signals to compiling structured datasets. Examples like Able 2744, discussed earlier, show how Webb's instruments reveal numerous faint arcs that Hubble could not capture, turning single cluster fields into detailed test grounds for structure mapping. The outcome is that arcs cease to be only striking visual features. They become validated coordinates marking where matter shapes the geometry of space. Each measurement contributes to a fuller map of the cosmic skeleton. The consensus view among astronomers is that Webb now provides the most capable toolset for this purpose, thanks to its combination of depth, infrared vision, and precise spectroscopy. What once required models and assumptions can now be grounded in sharper data and broader coverage. These clearer images and improved techniques, however, are only the starting point. Once arcs and galaxies have been observed and measured, the harder task is deciding what those signals really mean about the matter responsible for them. The interpretation is not always straightforward, and this is where debates and competing explanations begin. Interpreting the invisible. When arcs appear in Webb's images, the central challenge is to understand what they reveal about the universe's hidden mass. The mainstream consensus is that gravitational lensing primarily maps dark matter concentrations. Dark matter, the unseen matter identified through its gravity, remains the leading explanation. It does not emit or reflect light, but shapes the scaffolding on which galaxies form. Because it is invisible, its presence is tracked by how it bends light from distant galaxies. Lensed arcs therefore become markers of where dark matter gathers, hinting at the structure of halos and filaments. This interpretation is widely supported, though it comes with important qualifications. One source of complication comes from ordinary or baryonic matter. The stars, gas, dust, and black holes that make up familiar objects. These components can affect local gravity and therefore alter lensing signatures. Exploding stars can push surrounding gas aside, while actively feeding black holes can drive powerful winds. Each process redistributes matter and these motions are not always easy to disentangle from the smoother pull of dark matter. The influence is smaller in scale, but still significant enough to blur what might otherwise be a clear outline of unseen mass. The barred spiral galaxy NGC 1365 serves as an example of why this matters. Gas and stars within the galaxy move under many competing gravitational tugs. These flows create signatures that complicate models built only on the assumption of smoothly distributed dark matter. In practice, astronomers need to account for how baryonic processes can alter local conditions, even as dark matter dominates on larger scales. This makes the map of cosmic structure a layered picture. Visible matter adds surface features, while dark matter provides most of the framework beneath. Studies of NGC 1365 remain ongoing, and researchers emphasize that its behavior is a reminder of how ordinary matter must be included in lensing models to avoid misinterpretation. A further challenge comes from the models themselves. Lens models are the mathematical tools used to infer mass distributions from arcs. Different research teams make different assumptions, such as whether the dark matter is treated as a perfectly smooth halo, or whether small satellite galaxies and clumps are included. These choices can shift predicted outlines. While broad conclusions remain the same, the fine details, like the density of a filament or the presence of substructure, can differ by model. This highlights why mass mapping is not an automatic output, but an evolving approach shaped by assumptions about both physics and mathematics. To manage these variables, scientists rely on validation strategies. Multi-epoch imaging provides repeated observations of the same region, confirming that arc features are consistent and not simple imaging artifacts. Spectroscopy ensures that the galaxies identified as background sources really lie behind the cluster lenses, confirming their arcs belong in the analysis. Each measured redshift strengthens the reliability of reconstructions. Together, these checks make sure that the structures mapped are physical and not illusions of noise or coincidence. Cross-checks are equally important. Webb data can be compared with X-ray observations that show hot gas in galaxy clusters, adding another piece of the total mass distribution. On far larger scales, lensing of the cosmic microwave background provides an independent probe of matter. If Webb-based mass maps align with these other approaches, confidence grows. Where mismatches appear, models must be refined. These external comparisons ensure that cosmic Webb maps are not built on a single method alone. Some teams consider additional possibilities. Ideas such as hidden clumps of dark matter or modified laws of gravity remain hypotheses at this point. They are not required to explain most data and need stronger evidence before they can be considered. The default working hypothesis remains dark matter plus baryonic physics. Claims that require new physics demand careful confirmation through multiple instruments and independent datasets before gaining acceptance. This measured way of interpreting invisible structures forms the foundation for how current results are judged, but it also guides how future work is planned. The standards for confirmation ensure that cosmic maps will improve without resting on premature conclusions. With this careful framework in place, we can now return to the bigger picture, the universe shaped by mass, both visible and invisible, assembling into a recognizable geometry across cosmic scales. Conclusion: Webb's observations now show arcs and distortions with a clarity that older telescopes could not achieve, turning them into measurable points in the map of hidden mass. Each signal helps refine how we understand clustering on cosmic scales, from galaxy groups up to filaments spanning billions of light years. These maps let scientists test models of structure formation, choose high-value targets for future deep surveys, and tighten constraints on how quickly matter clumps over time. If you've watched this far, leave a comment about which question on the cosmic web you'd most like explored next, and subscribe if careful. Evidence-based explanations of Webb's discoveries are valuable to you. Key takeaway: Webb expands the set of reliable lensing markers and strengthens our ability to map invisible mass, while continued validation and modeling remain essential.